All right, we got a little behind in class today, and you didn't have as much time to work on those questions and problems as I would have liked. But I hope that you did those outside of class. I'm making this video just to make sure that you can check your work, to make sure that you have a good understanding of what we've done so far. So our first question/problem went back to the scenario where Jill was delivering flyers up and down her street. And we did have information from that earlier in the slides from our lecture today. So you might want to reference those for answering this question. Basically, this is helping us make sure we understand how to calculate average velocity. So average velocity is just displacement over time interval. So for the first 9 minutes, in 9 minutes, what we found was that the displacement of Jill was 1/2 kilometer. If we want to find the average velocity, we can take that 1/2 kilometer displacement over 9 minutes, and that will give us our average velocity. I don't even have a number for this, but what I want to make sure is we know what numbers we're working with. After 18 minutes, she actually gets back home, so her position is 0. So our displacement for the first 18 minutes ends up to be 0, which makes our average velocity 0 as well. Then she actually goes down the street after she comes back home, and then she goes down the street a whole kilometer, and that takes 15 minutes. And so between 18 and 33 minutes, her displacement is actually 1 kilometer, and it takes 15 minutes. So those are the numbers that we would divide to find her average velocity for that time. And then finally, she ends up here at the end, and I believe that her total time is, I think it ends up to be 58 minutes. And so at that point, she's at minus 0.75 is her position. She started off at 0, and so that's our displacement, and we divide by 58 minutes. So our average velocity will be found by taking minus 0.75 divided by 58. I did mention on this slide that just to make things easier, I didn't expect you to change your units to meters and seconds as we normally would, but we could keep it in kilometers per minute just to make things easier for this particular problem. Now, here's a case in this question where we're trying to find the average velocity to see which one of these graphs gives the biggest average velocity, but notice it says magnitude of the average velocity, which actually means the absolute value. So we're not really worrying about positives and negatives here. We're just looking for the biggest value. We don't have any numbers on these graphs, but we do have blocks. And so we can just do rise over run using numbers of blocks. So in trial A, our rise is 3 blocks, and we have 1, 2, 3, 4, 5, 6, 7 blocks in the run. So our average velocity is 3/7. In trial B, we have a rise of 6 blocks. Again, the run, or what our delta t is, 7 blocks. So we have an average velocity of 6/7. That's our slope. Here in trial C, we have a horizontal line which has a slope of 0. And in trial D, it actually has a negative slope of 6/7. But then when we're answering the question and it wants to know which trial has the largest magnitude of average velocity, Both B and D answer the question because when we're considering the magnitude, we don't worry about the negative sign, and we're just looking at both of these have a magnitude of the average velocity of 6/7. In this graph, it's just making sure we understand how we find quantities from a graph. It's a position versus time graph, and it wants to know of the 4 points that have been located on our graph, which one has the greatest or most positive velocity. Keep in mind that that would be the slope of the tangent line at each point would give us the velocity, and we could have Q will be 0, and so will S. The tangent line would have a slope of 0. The slope at R would be relatively steep, but it would be a negative slope, and we want a positive slope. And we're left with point P is the only one that has a positive slope, so it becomes the default answer because the slope of the tangent line at point P would be positive and would indicate the instantaneous velocity at that time. Now we have a couple of questions. Actually, these come from your textbook, but we can also practice them, making sure we understand stuff about our graphs and how we get information from it. This graph is actually kind of sneaky because it has 2 lines on it. The red line represents a graph of the speed or velocity as a function of time, and the blue line represents the position of this object as a function of time. So both of those pieces of information are on the graph. The question that they ask is, which of the following describes the motion of the car at t equals 10 seconds? 10 seconds is at the end, and so we're looking here or here, depending on what we want to get. If we look at the question, we can get we can sort of narrow it down using either one of the graphs. Both of the graphs would tell us that we would have a positive velocity, and it does seem that as we are going from 4 seconds to 10, the slope of the blue line is getting bigger, and we also see that the velocity graph is also growing. We see that the velocity is positive, as is the slope of the position thing, so we know that it's moving what we would consider forward. So it's moving forward, it's getting faster, and so we can use this to sort of determine which answer A, B, C, D, or E is correct. Not moving definitely isn't, and anyone that says backwards is not correct. And remember, so we said the car was moving forward because of the positive velocity and the positive slope of the position graph, but we also said that the velocity was getting bigger. So we would then narrow down from our 2 remaining choices that C would be the correct answer. Now we're using the same graph, but we're looking at a different time. At about 4.6 seconds, this is at this location. And we can see 2 things using the 2 different curves. We can see that the slope of the position graph here is 0, but we also see that the velocity line crosses through 0. So we're getting that information in 2 different forms. And so if the velocity is 0, the car is not moving, it's not going forward, it's not going backwards, we would say it was not moving. Now, now it's the same question, but now we're focused here at t equals 0. The car is moving definitely because the slope of the position graph is not 0. We also see that the velocity has a value. It's negative. So now we know at this time the car is moving in the backwards direction. So we get rid of our forward answers and we get rid of not moving. Is it speeding up? Well, if we look at the slope of the position curve, it's becoming less steep. So that corresponds to a smaller speed and a decreasing velocity. But we can also see here, while it is going up, what's happening here is the car was moving in the negative direction or moving backwards. But as we go from 0 to longer times or later times, we can see that it's becoming less negative. So it is, the car is slowing down. It's not speeding up, because speeding up is referring to acceleration. So it's actually going to slow down. It's going to come to a stop, and then it's going to increase in the positive direction. So we're going to answer part B. Now we're going to get a chance to do a little bit of math. This is really similar to the problem that I did in class, except that it's a different expression. So hopefully that example from class would help you. As we find displacement and average velocities, we're going to put values in for time. So to find the displacement is looking at putting in t equals 4 seconds and then t equals 2 seconds, and we subtract our two values. So x at 4 would be equal to 3 times 4 squared minus 4.5, put in 4 for time, plus 4, and we would get the position at 4 seconds is 34. Sorry about that. At 2 seconds, we would get 3 times 2 squared minus 4.5 times 2 plus 4. We're just plugging in t equals 2 for the time, and we get a value of 7. So the displacement is going to be 34 minus 7, which is 27 meters. For the average velocity, during this time interval, we take the displacement over the time, so we get 27 meters, and it's 4 minus 2, which is 27 meters over 2 seconds, and so that is 13.5 meters per second is our average velocity over that time interval. To get the instantaneous velocity, remember that's the derivative of the function with respect to time, we would get 6t minus 4.5, and then we're going to evaluate that at 3 seconds. And we turn out that it is the same value. I think that what we're finding is that basically, because we're looking at a time in the middle of our average interval, and because it is actually accelerating at a constant rate, which we'll be able to see after we learn a little bit more next time, it kind of makes sense that we would get the same value. All right, now here is a problem I chose because it also is going to work a little bit with the ideas of distance and speed in terms of our definitions that we learned about. So the question is, a swimmer is in a 50-meter pool. They're going to do the first 50 meters of the 100 freestyle in 38.2 seconds. At the end of the 50 meters, she turns around, swims back to the start. So that length of 50 meters takes her 42.5 seconds. It asks us to find the average velocity and speed for the leg from start to the far side of the pool, for the return leg, and for the total trip. So for the first part, we just do displacement over time is 50 over the time, which is 38.2, and I get 1.31 meters per second. Now, something we might not have thought about for the second leg is because she kind of goes from this end, she goes down, and then she turns around again. So for the second leg, her displacement is minus 50, and the time is 42.5 seconds. And so the average velocity for the second leg is negative. We want to be careful that we pay attention to that. And then for the whole trip, actually, of course, her displacement is 0. Her total time is the 38.2 plus the 42.5. Doesn't really matter because her average velocity is 0 meters per second because of the fact that she begins and ends at the same location. Oops, sorry. For her speed, the speed is just the speed is going to be just her magnitude of her velocity, so we would just use 1.31 meters per second for the first leg and 1.176 meters per second for second leg. And for the total trip, I should have said the average speed, because in that case, we just wanted to sort of look at the fact that she goes 100 meters for the entire time. So this is the distance. So when we say the average speed and over the total time, and that would be a 1.24 meters per second. All right, so that's kind of comparing like how we might use distance and speed and velocity, kind of contrasting those definitions. And then finally, we have this expression, the position of an object, and it's given by this expression, 5 plus 4t minus 2t squared. And we want to answer some different questions. The question here is, how many times does the object pass through the point x equals 0? And then what direction is it moving at these times? So how would we answer those questions? I think the first part is relatively more straightforward to see that we just want to know when does x equal 0. So we'll set this equal to 0. And you could either maybe have your calculator programmed, or you simply do it old school and use the quadratic equation. I did the quadratic equation and kind of moved it around because I don't like the negative signs in the front. And so t is negative b, so it's 4 plus or minus the square root of 4 squared minus 4ac all over 2a. And we get two possible answers for this. We get 2.87 seconds and minus 0.87. Those are the times when that equation is equal to 0. This we eliminate because we don't deal with negative time, so it makes no physical sense. And so we know that the object will go through x equals 0 at 2.87 seconds. To figure out the direction it's moving, we would look at the sign of v, because if v is positive, it's moving to the right. If v is negative, it's moving to the left. Keep in mind, we find velocity by taking the derivative of that expression with respect to time. And we'll get 4 minus 4t. We will put this value in here at that time. If we have v at t equals 2.87, we get 4 minus 4 times 2.87. It gives us minus 7.48 meters per second. And the negative sign means that it's moving to the left. All right, so please try to do these on your own and check your work using this video, and we will continue with this material next time I see you.